This video is on type 2 ionic compounds, how to name them and how to come up with a chemical formula for them. So type 2 ionic compounds involve a metal and a nonmetal, because remember that an ionic bond is between a metal and a nonmetal. Remember that a metal can be called a cation. So a metal can be called a cation, so that's pretty much the same thing, right? And a nonmetal can be called an anion. The important thing for it to be a type 2 and not a type 1, the metal has to be one of ones that has two possible charges. So when we look at our table of ions, you'll see that the table has some, for instance, like iron, that can be split in two, and the box will look like this. Unlike our, let's say, calcium, that only has one possible charge. It can only be 2 positive, where iron could be 3 positive or it could be 2 positive. So calcium cannot make type 2 ionic bonds, only things that have 2 possible charges or split in 2. Another way for you to identify it is by looking at the name. So if you happen to see it written out as, for instance, iron 3 oxide, whenever you see the Roman numerals, that Roman numerals tell you that it is a type 2 ionic compound. If there's no Roman numerals, it either is covalent or it's a type 1 ionic compound. So remember, here is our periodic table again, right? And here is our staircase. And remember again that all of the metals are on this side, right? So everything on this side of the staircase, this way, because these are all positive, are metals. But we're only concerned today with these ones that have 2 possible charges. Those are the only ones, again, that are going to make type 2 ionic compounds. And remember that they have to have one of these, ones that are all split in 2, with one of these non-metals. Remember that these are called anions. So remember to check first to make sure that it is ionic. So you're going to make sure that you can find a metal on this side of the staircase, and make sure that you can find a non-metal on this side of the staircase. Make sure that it is one of those ones that is split in 2, so the box is split in 2, meaning that it has more than one possible charge. If it is, then it's going to be a type 2 ionic metal. There's another really important point I put with a whole bunch of stars here so that we remember. Anytime the Roman numerals there, the Roman numeral is always going to match the charge. So if it is a 3 in Roman numerals, that means it's iron 3 positive. If it was a 5, let's say, so if it said 5 for something, that would mean it was 5 positive. If it is 4, that would mean it's 4 positive. So the Roman numeral is always going to match the charge. So iron 3 phosphide would look like this. Because iron is 3 positive and phosphide is 3 negative, they essentially cancel each other off, and we just get FeP. We're going to do some more examples. Okay, so these examples of compounds to name. So the first one is SnCl4. So I have to look up what Sn is first, and I find out that it is tin. When I see where tin is, I can see that tin is split into 2. So tin looks like this. So it's 4 positive on the top and 2 positive on the bottom. Okay, now my job is kind of to be like a detective here, because I got to figure out which tin it is. So if it was, could be this one. If I look at chlorine, I see it's negative. If I look at, if it was 2 positive and chlorine was negative, it could be this one. I can see obviously that it's going to be tin 4, right, because the 4 would have had to move down here. So this is tin 4. Just so that you can see, if it was tin 2, it would look like this. And it does not look like that. So it's tin 4. And then remember that this is called chloride, that the ending changes. So this is normal as you find it on the table of elements, and this one changes to ide like you find it on the table of ions. Okay, next is FeBr3. So Fe can be Fe3 positive or Fe2 positive. So again, to be a detective, I look at what number is over here. I think about, okay, it could be this combination or it could be this combination. Well, if it was this combination, I would get FeBr2, and that does not match that, right? So it's not Fe2. That means that it's iron 3. I would write bromide after. Okay, next is CrO. So Cr is for chromium. Chromium can be either 3 positive or it can be 2 positive. And oxygen is now called oxide. So now my choices are, it could be 3 positive or 2 positive. So let's check that out. So if it was 3 positive, notice that the 3 would go here and the 2 would go here, so I get this. That doesn't match, right? So it can't be that one. Let's just make sure if it was 2 positive and this was 2 negative, I would indeed get this, which does match that. So it would be chromium 2 oxide. The next one is Cu2S. So copper is what Cu is. Oops, didn't like that one. So copper looks like that. And so it could be either copper 2 or copper 1 positive. So if it was copper 2, let's see, and sulfur becomes sulfide, it's 2 negative. Well, that would give me this. That doesn't match that, so that can't be copper 2. So it has to be copper 1 sulfide. Remember that all type 2 compounds are going to have this Roman numeral in them to indicate which one of the compounds we're actually using or which charge we're actually using. Okay, next we're going to try having from the name to the compound. I think I did that backwards. The last one we did from the name to the compound. So this one we'll actually do from the compound to the name. Okay, so I came up with some examples where we have the name and we have to come up with the compound. So the first one is Cobalt 2 nitride. These ones are easy to identify that they're type 2 because, again, they have the Roman numerals. So right away I can see that they're actually type 2. So cobalt symbol is CO. And maybe I want to go over here and do it on my scrap paper, but cobalt is 2 positive. I can tell it's 2 positive because it has a 2 Roman numeral. Nitride is N3 negative. So you can see that the 2 is going to trade places with the 3, right? So it becomes cobalt 3 N2. And so this is the formula for cobalt 2 nitride. The next one is manganese. It's not magnesium, but it's manganese, which is a different element here. So manganese is actually Mn, and so when I look at manganese, you'll actually see that it is actually split into, it can be 2 positive or it can be 4 positive. One of the important things is if you had to guess for some reason, the only reason I'm thinking you have to guess is if I put iron reacts with, I don't know, hydrochloric acid, and figure out that, iron is going to go with chlorine after. if I had to guess what kind of iron it was that went with chlorine after, you always want to pick the one on the top, because again, the one on the top is the most commonly occurring one in nature. So if you have to guess, or if you have no idea, the best guess is actually the one on the top, because that's actually the most commonly occurring one in nature. So manganese is Mn. So on my scrap paper I'm going to be doing this. It has a 2 positive charge, because that's what the Roman numeral is. And it's with sulfide, which is 2 negative. Because this is 2 positive and this is 2 negative, I actually get this. So MnS. Okay, the next one, remember that you can pause the video at any time. Make sure that you can do them first before I do them, and make sure that you're on the right track. Lead is Pb. It is lead 1. Sulfide is 2 negative. And so I'm going to get Pb2S is my final formula. Remember again that this is kind of something that you're going to do on your scrap paper that I'm not going to see, right? Because when you finally come up with a compound, it should have no charges. I should see no superscript numbers up here. I should see no positives, no extra numbers up at the top of it. The next one is lead 4 oxide. This is a good one to do because this one's kind of tricky. So lead 4 would be Pb4, and oxide is 2 negative. Now you would think that normally it would be this, but there is this rule about that if these two things can be divided by the same number, whether it be 2 or 3 or 4 or whatever, but if they can be divided by the same common factor, that we actually do that. So this becomes 2 instead, and this becomes 1. So instead of it being actually Pb2O4, which is actually wrong, it actually becomes PbO2, which is actually the correct formula for it. So this one is kind of a trick question. So you might want to make a note of that, that when they can both be divided by the same number, that we actually do that. Next, we're going to try some compounds to name with polyatomics. So the compound to the name with polyatomics. Okay, so here are some examples of type 2 compounds with polyatomics. So the first one is Fe and then brackets NO3 with a 3 subscript. So Fe is for iron. NO3 is something that we're going to find on that polyatomic chart. So it's going to be on the table of ions. It's in a little box at the top. So NO3 I'm going to see is called, let's see, Niri. So it's nitrate. Remember that all polyatomics are going to have a funny ending to them, right? So they're not going to end in IDE, except for, of course, hydroxide, but they're going to end in ATE or ITE. Now the only thing that we're missing is our Roman numeral to say which kind of iron. So think about it for a second. You might want to even pause the video if you need to, but is it going to be iron 3 or is it going to be iron 2? Okay, if you have to think about it, right, here's iron 3 positive, NO3 can only be negative. So if it was going to be 3, okay, that kind of fits what we have here, right? If it was Fe2 positive with NO3, what we're going to get is actually this instead, the 2 down here. So that tells me that this is iron 3 here. Okay, we're going to move down to this one where it's lead and NO3. So again, that is nitrate. Pb stands for lead. So the Pb actually comes from the Latin form of lead. And lead has 2 possibilities. It can either be 2 positive or it can be 4 positive. So if it was 4 positive, do you think that we would have this 2 down here? Remember again, here's the possibility. Here's Pb2 positive, NO3 negative, and here's Pb4 positive, NO3 negative. The 4 is going to go down here, right? So this one would become this, with the 4 in the subscript. Whereas this one becomes this, with the 2 in the subscript. So this one matches the one, right? So this one is going to be lead 2 nitrate. Okay, next is this one. So MnMnO4. So Mn is for manganese. And manganese has two possibilities. It can either be 2 positive or it can be 4 positive. Okay, and I just want to make sure that when I look at MnO4, which is actually called permanganate, permanganate's possible charge is that it can be, it can only be negative. Okay, so Mn can be 2 positive or Mn could be 4 positive. Remember that if it's 2 positive, am I going to end up with a 4 down here? Not likely, right? The only way that I'm going to end up with a 4 down here is if it was 4. So it's Mn4 or manganese 4 permanganate. Okay, the next one is Cr2SO3. So Cr, I'm going to find out, is for chromium. Chromium can either be chromium 3 positive or it can be chromium 2 positive. So those are my choices. SO3 I'm going to see is for sulfite. And again, that's a polyatomic, right? So this is many atoms all collected together. So let's see. Sulfite is 2 negative. And if, let's say, I pick chromium 3 positive, see that the 3 would go down here, right? And the 2 would go over here. So this is indeed chromium 3 sulfate. If it was chromium 2, what would happen is that they both cancel out, so we wouldn't have any extra numbers. It would actually look like this instead. So this is chromium 3 sulfite. Okay, the next one we have the name, and we're going to go up into the compound. So these are again with polyatomics. So on this last page of examples, we're going to go from, again, name to compound with the polyatomics. So the first one is nickel 3 oxalate. So I'm going to have to look up what nickel is, and that nickel is 3 positive. Oxalate, again, I'm going to find, noticing that it ends in ATE, so that's one of the ones I'm going to have to find on top of the polyatomic chart there, is Cr2O4, and I'm going to see that its charge is 2 negative. So again, these numbers are just going to switch places, right? The 3 is going to go down here, and the 2 is going to go over here. Now notice when I write it out, do I want to write it like this? Okay, the answer is actually no, right? Because right now it looks like I have 43 oxygens, which is not good. So you want to make sure that you put these brackets in here to indicate that you just want 3 of the oxalate molecules. So there has to be brackets in there. And again, if I was to count out all the things in here, if I said to you how many nickels are in here, there's 2 nickels. If I asked you how many chromiums are in here, there's 3, right? Because the 3 gets multiplied by this. So there's 3 chromiums. If I asked you how many oxygens are in here, there's actually 12 because you go 3 times 4, so there's 12 oxygens in there in total. Okay, the next is zinc sulfate. So remember again that you can pause the video anytime if you want to and try them on your own and see how you do and see if your answers compare to mine. So zinc sulfate. What do you notice first off about doing zinc sulfate? Did I have any Roman numeral in here? I wanted to see if I could actually trick you up, but there is actually no Roman numeral in here. So zinc sulfate is actually, zinc is still a metal, so it's still a metal. Sulfate is a polyatomic. It is negative, however, so that it still makes it a non-metal. So this is still ionic, but it is not type 2, it's type 1. So when I write this one out, it doesn't have an ionic or a Roman numeral in here. but it kind of do it the same way, right? Zinc is 2 positive. Sulfate, I'm going to find, when I look at it, is actually 2 negative. So this is 2 positive, this is 2 negative, so they cancel each other off. So I write ZnSO4 is my total formula. Okay, next example is antimony 5-phosphate. Antimony, we'll find out, is Sb. 5 means that it would have had a 5 positive charge. Phosphate is PO4 3 negative. Now when they go together, what's going to happen here is that the 5 is going to go down here and the 3 is going to go over here. So what I'm going to get is Sb3 PO4, and again I need to have brackets around here, with a 5 right there. So this is what antimony 5-phosphate is going to look like. The next one is titanium 4-hydroxide. So hydroxide I know is OH negative, and titanium 4 is going to look like Ti with a 4 positive. Okay, when they go together, I'm going to get TiOH4. No, right? Because I need to have brackets around here. This is really common to do, especially with hydroxide for some reason. If I ask you what sodium hydroxide is, that's fine. But sometimes if I ask you like what barium hydroxide is, these are not type 2 by the way, but they're type 1. But barium hydroxide, remember, barium is 2 positive, hydroxide is negative. You don't write this, right? It has to actually have the brackets inside it. This is a really common one to mistake. Can you imagine the difference though in molecular mass if we're talking about this versus this one? When I look at this one, I see that I have 1 barium, I have 2 oxygens, and I have 2 hydrogens here. If I look at this one, which I wrote incorrectly, it looks like I only have 1 barium, 1 oxygen, and 2 hydrogens. So my calculations would turn out a lot different depending on which way I write it. So the brackets do make a huge difference here. Okay, hopefully this will help you get started on some naming and some review homework.